All right, for today we're going to find the inference of regression. So we're going to interpret regression in residuals by a calculator. Please note that this won't help you on my math lab because those require you to do it by hand, which we'll see tomorrow. So, I wonder whether the data of ice breakup in Nenana has changed over time. The slope of that change might indicate climate change. I have the date of ice breakup annually for 95 years starting in 1917, recorded as the number of days and fractions of a day until the ice breakup. So here's my data, right there. I'm going to develop a null hypothesis with saying that there is no change in the data of ice breakup. So my alternative is that there is change. First, let's check a couple of conditions. Straight enough. Is this data straight enough? Does it look kind of straight to you?
No.
No?
Not at all.
It does look very spread, but here's a question. Would you say this is more linear than it is anything else?
No.
No. What would you say it is?
It's random.
It's random.
Well, obviously it has to be straight because we have to continue with the problem.
All right, well, I mean, the point is to debate and discuss. So if, let's say you're saying it's not straight, perhaps you would want to continue anyway. And then just note, I don't think this satisfies the straight enough condition. And maybe somebody else comes in afterwards and says, well, to me that looks straight enough. To me that looks like there's some kind of,
Straight line is just spread out.
straight line is just spread out. Somewhere these are going to be averaged, right? And does that average make a line, or does it make kind of a, maybe a U? Does it make kind of a squiggly? Whatever. So the point is, what kind of regression, what kind of trend is this data doing? By not straight enough, that is definitely not straight enough. So here's an example of what you're looking for that will definitely fail. Josh, right there. This is not straight. Notice there's a curve to it. Do you see any curves here? Yeah, it's pretty spread out, but I don't see any kind of trend going like this.
Consider it as straight.
Or like this. So this will definitely not be straight. I agree. This is pretty spread out. But perhaps the key word here is
Straight enough.
enough. Maybe that's why they added that in there. Straight enough.
That's
Give
a
or take.
condition. Just straight enough.
Independence. I would say the ice spread each year is independent from another, maybe. Each year has different climate changes than the previous year. Random residuals condition. So look at my residuals. Do they look kind of randomized? I don't see any trend going on. Looks pretty randomized. Randomization condition. I'm not exactly picking my ice breakups by random. So it wouldn't exactly fit this one. But again, like we've seen, it's okay if you don't meet all. You just have to make note of it later in your conclusion. I mean, not much we could do. I mean, we do have 95 years of data. We could just pick a couple samples from those 95 years. And then that would satisfy this condition. Next, equal equivalence assumption. Does the plot thicken condition? Meaning, do you have some kind of trend that where it gets small and then it spreads out? Or again, is it kind of just evenly distributed?
Evenly random.
It's evenly random, yes, I would agree. And then nearly normal condition, where you have to look at the residuals and see if it matches a normal model. Do my residuals match that?
Mm-hmm.
They do. So it looks like I'm good to go except for random, which is exactly what the book said. So straight up, I have quantitative data with no obvious bend. Maybe this is what we're really looking for. Is there a bend in this data?
So if there's no bend, it's a yes.
Pretty much, yeah. Independence, these data are time series, which raises my suspicions that they may not be independent. To check, here's a plot for residuals against the time. That also matches with the random residual condition. I see a hint that the data oscillates up and down, which suggests some failure of independence, but not so strong that I can't proceed with the analysis. So, meaning, do appear some little bit outliers here, but not enough to just fill altogether. Randomization condition, again, we said this is not random. We're just taking all the years as they come. Does the plot thicken? The residual plots show no obvious changes in the spread. Looks pretty even. And then near the normal model, no outliers. Looks like a normal model. Not very skewed. We're good to go. All right. So I'm going to show you how to calculate this if you're given the table. Put in the calculator to get the data here. Tomorrow I'm going to show you if you're given this data, because this is what my math lab gives you. It gives you the data and asks you to interpret things with that data. What do we have here? So I see my P level is very small. That's the first thing I want to look at. With it that small, I'm going to reject the null hypothesis and conclude that there is strong evidence that on average the ice breakup is occurring earlier each year. But the hint of an oscillation pattern in the residuals raises some concerns. So again, we're going to run a t-test. T-test is going to give us a p-value, and we're going to use that p-value to reject or fail to reject our null. But just FYI, this is how we are going to set this up. Notice here is my regression model where I have my date equals, this first number here represents my 0 because I've been minus 0.071 years since 1990. You see, it's a subtracting. So this is where I'm getting this part. It's occurring earlier each year. I'm subtracting here, and I'm adding my year here. So if the year was 0, then this represents where my ice is at 0. This first number here. B value. This is going to be your B value with your regression line. So B plus AX. This is my initial. And this is my, let's say, I guess, rate each year. How much am I decreasing each year? So it looks like I'm decreasing at 0.071. Are we talking about degrees? Degrees each year. No, days. Sorry. So 0.071 days each year that my ice is breaking up. Yeah. So first value that you come up with your regression line is your initial value. It's where you start at 0. And then the next one next to your variable will be your rate. And notice if you see a plus or a minus, plus means I'm increasing based on the initial each value of x, or I'm decreasing at a rate of the value of x. In this case, since we're talking about years, I'm decreasing each year at this rate. So I think this interpretation helps you with problem number 5 on my math lab. Now let's look to see if we're given a table, how can we calculate our p-values with the regression. So let's use the data from Chance magazine for 11 of the top performances in women's marathons during the 1990s. Let's examine the influence of temperature on the times for elite runners. So go on your calculator and do stat edit. L1, you'll want to put the temperature, 44, 46, all the way to 65. L2, put in the timed run. Note our null hypothesis, usually it's going to be there's no change. So we're saying there's no change in the data of times for runners based on the temperature. And our alternative is saying yes. Temperature does affect our runners' times. Hold off on this. Just put in the L, put in the table in your calculator. Okay. Hopefully you have it in there by now. So stats, edit. This should be your table. Now let's go to stats, test. Let's calculate our p-value. Let's do our t-test. Go all the way down to F, linear regression t-test. Hit enter. L1, L2 frequency, I'm saying it's not equal, my null. And this part right here, just like I showed you yesterday, you can put in that regression equation into your y equals so you can graph it. How to do that? Again, is go to vars, y bars, function, and y1. Yep, it's very much hidden within the calculator.
You can just use alpha trace.
Alpha trace. Alpha trace, or you could do that.
Genius.
That is genius. I forgot about that. Let's do it the hard way. Oops. Okay, just go up. I can't go up. Good. And calculate. Gives us lots of data here. Lots of numbers to use. But mainly, let's look at the p-value. What does the p-value tell me? Do I reject the null or fail to reject the null?
You failed to reject.
I failed to reject the null. It's a very large p-value. It says based on my data, it's going to happen about 29% of the time. So decent chance that my data is just a coincidence. Notice it also gives you your equation, y equals a. So 1.41, that's my initial, that's my initial time here of what I started with. So what did we start with in 1990? So let's say 1990. The initial one was 141. And then each year, is it increasing or decreasing? With a b value of 0.03. Just think, is this number positive or negative? Positive. So each year I'm increasing by 0.03, or basically 3 seconds. Which, if you look at the data, does look like it's gradually increasing there as the temperature increases. So at my original temperature of 44, I have 41. So remember, the data can go backwards to account for the 0. Oops. And yeah, here it is. So with this large p-value, we are going to reject the null. Looks like there is a difference between the temperature and how fast the runners are running. Looks like as the temperatures increase, so are the times. So I guess they're not as running as fast, right? It's taking them longer to complete the marathon. 142 minutes, that's pretty good for a marathon. 31 miles. They're trucking it. Now let's try to find a 95% confidence interval. So you've already entered the data in the table. Now let's go to stats, test, and right below linear regression test, linear regression t-interval. Hit enter. Everything should remain the same. Again, you're given the option to input the regression line into y1. 0.95 for my 95% and go. Looks like I am 95% confident that my runners will have this difference between their times based on the temperature. So they'll either be less or faster than 3 seconds or slow as, let's say, I guess 10 seconds based on the fluctuation of my temperature. And again, all these numbers should be the exact same as the t-test. Only now we're given an interval instead of a p-value. Where is my mouse? All right. Now, with this, we should have run several tests here, right? Straight enough condition, independence assumption. Let's go ahead and look at the data again. So I want to go to stat plot. Let me turn this plot on. Let me turn it on there. I want to change this to, sorry, I had this set for something else. List, okay, so by default yours should look like this. And if I hit graph, zoom stat, there we go. Here's my data. Notice it put in my regression line. So, would we say this is straight enough?
Sure.
Sure, yeah. Well, do you see any kind of bend?
No.
No, not really. Kind of hard to tell, but I don't see anything. Next, independence. I can assume that each temperature is independent from itself. Each run is independent from the other runners. Let's assume that the same runner read each of these. Otherwise, that wouldn't be very good, would it? Some runners run faster than others. But I guess this is on average, right? Or no? No, top performances. Okay. Let's see. Random residuals condition, randomization condition. It didn't pick random runners, it picked the top ones, so it kind of fills there with my randomization. Right? And the residuals, we'll have to run a residual chart here in a minute to check on that. So this is on pause. Does the plot thicken? That, a little bit. I mean, it is thicker out here and it kind of narrows a little bit, but we'll check the residuals as well. And the normal condition outlier. So a lot of these deal with graphing the residuals. Now let me show you a trick that I just learned yesterday. Instead of doing the residuals by hand, there is a way for the calculator to calculate for you. So let me take away my regression line. Now I want you to go to second plots, go to plot 1, change this to a histogram, go over here to XList. So we're doing this right here. Second y equals stat plot, turn plot 1 on, type histogram, and for XList, go to second stats. So I'm going in here in the list and go all the way down to RSID, residual. It's going to plot the residuals of the data you have put in to your stat list. And hit graph. Well, you might want to go zoom stat, and bam, there's the histogram of your residuals. Would you say that's nearly normal? Yeah, I mean, there's a little bit skewness, but not so much to where you're just like, nope, failed. I don't see any outliers, so I would say it passes enough. So there's a neat way to graph your histogram of your residuals instead of doing it all by hand and then had to enter it into stat edit.